Hello and welcome to How to Measure Latency at the P99 Conference 2021. Thank you very much for showing up, and thanks to the organizers for letting me speak at this beautiful event. My name is Heinrich Hartmann. I'm a principal engineer at Zalando working at the SRE department. And I'm going to start off with some motivation and background for this talk. So I personally have been talking about statistics in the operations domain for the better part of 5 years now. I have been working for a monitoring vendor called CONF in the past, and they have a very latency-focused product. And I took it as my task to explore the mathematical aspects of monitoring and operational problems, and published quite a few blog posts and articles, and even one paper about a histogram data structure. So inspiration for this very talk comes from a series of talks by Jill Tini, which dates back to 2013 to 2015, where he was talking about how not to measure latency. And this talk is actually insanely great, and I watched it like 5 times, but I still didn't completely get all the details. So this conference was the perfect excuse to really go through it and find what's there and update it to the newest version, 2021 version, and share it with this audience. So this was the plan for this talk, and we will see how far it is a success for those who are familiar with Jill's work. One very nice coincidence here is that I just today came across the P99 conference blog, and there's actually a very recent article, just 2 days ago, it was published, on coordinated omission. And coordinated omission is the concept that Jill introduced in that how not to measure latency talks. And just seeing that up there at this very point in time made me smile, and it's a very good blog post going into much more depth than I will be able to cover in this 20-minute session. So here already a shout out to that blog post. It's slow. It's the hardest problem you will ever debug. It's a saying by Theo Schlossnagel from Seconus, my former boss. And this resonates a lot with me and actually sets the tone for this presentation quite a bit. There are latency problems. If you have them, they are hardly ever reproducible. The telemetry information you have to really understand where the latency comes from, it's very hard to get. And sometimes you even have conceptual mistakes. You think you look at something, but you're actually looking at something slightly different. And that difference turns actually out to be very relevant for the very problem you are debugging. And this is where coordinate omission and this kind of difficulties in measuring latency lie. And this is the focus also of this talk. I'm not talking about like the best tools to measure latency. I'm talking about the concepts behind it and what it entails and what you want to do right in order to have proper measurements, so you can do methodological debugging of your problems. So let's dive right in. We should probably first talk about what latency is before we talk more about how to measure it. Well, you have a certain operation in a computer system that has a certain start time and a certain end time, and then the difference between those timestamps is a latency. Well, to get the timestamps, you need a clock. I mean, there are some subtleties on computer systems with clocks that I will briefly talk about. Most important thing is that you are measuring it at a single computer system. You are not measuring the start somewhere and the end somewhere else. That will probably always lead to inconsistencies which are hard to square. But besides this, there's, from a theoretical perspective, that's really all there is. In the code, it actually looks fairly similar. Well, when the operation starts, you record the current time, and then when the operation ends, you're also recording the current time and taking the difference. This will give you a latency measurement. Few things to watch out. First, make sure you're actually measuring or taking the timestamp when the operation ends. So if your code actually has early returns or exceptions, then you need to catch them. And some languages give you facilities to do so. Another aspect of it is which clock is used. You want a high resolution monotonic system time for this applications, which is like the recommended thing. Monotonic, you don't want to have backwards jumps of your time when NTP hits. And a system time is as opposed to thread local CPU time, which is also sometimes interesting, but you have to be cautious of what you're getting. Python has a time monotonic function, which seems to be well suited for this. Also, PEP 418, which is linked here, which introduces the time monotonic function, is doing a very great job of explaining all the different available clocks on Linux, Solaris, FreeBSD, and ARM and x86 systems. So this is a very good reference if you want to deeper here and figure out what the best available clock is in your system. Measurement overhead, also something to be wary of. The execution of both code lines, of course, also takes time, and you have to be mindful of how much additional latency you're introducing in this way. My rule of thumb here is that for measuring I/O latencies like network or disk accesses, usually don't have a problem. For measuring CPU-bound workloads, yes, you care about this a lot, and micro-benchmarking, of course, usually does a few 100,000 runs of functions before it takes the measurement, exactly because the measurement overhead otherwise would skew the measurements. The last point is also very generic. In software engineering, it's always good to abstract things which have some complexity, and there's a little bit of complexity here. So we have made good experiences with having at-timed decorators or tracing decorators. In general, tracing libraries are a thing to check out. Measuring latency is oftentimes actually best done with traces because they actually give you a lot more. If you can get away with using tracing, then most of this is solved for you. There's one more slight subtlety that I will always touch here is when you're monitoring latency, so capturing latency information over longer time periods, there is two timings which are kind of interfering, which is the timing of the operation and then the timing of the reporting window, which is currently active. So the reporting minute is probably something like 10 seconds or a minute. And then the question is for the operations that take time or overlap with this reporting window, where do you attribute them actually to? And there are no silver bullets here. You have to make like choices. The only thing I would tell you right now is no matter what tool you use, explore these choices, know what the choices are. So how are operations attributed that are like intersecting with that boundary of the reporting window? And if you have 15 or so requests that are just very, very long and lurking there, how do your measurements look like? And if you understand that, then you will be in a good position to understand your signals here. So that's it. That's all I have for measuring latency. There is really not much more to it. The basics are there. So, but of course, this is not quite the end of the talk. There's more subtleties that we will discuss, and they're actually mainly concerned with where actually to measure latency. So in the distributed systems, we are usually interested in client-server interactions, so request-reply interactions between the client and the server component. And you have some like choices to make. Where are you actually measuring it? And also from a theoretical perspective, the system is super simple. Yeah, you're shooting a request and you're getting a reply. But if you dig a little bit deeper, then there is a ton of complexity that lies behind even such a small system. So if you follow through quickly, you have application code that makes a request, then it passes through the runtime, through the operating system. There are some queues here in the TCP/IP stack. Then you have hardware, which is also some buffers. Then you have network gear in the middle, and then the reverse thing on the other side. And everywhere are queues. And queues always introduce latency, like some amount of latency. And it's pretty hard to observe this kind of latency sources. I've actually made an effort to understand how much is in the Apache buffers, and trying to understand where the operating system queues stuff. And there are some metrics which you can get for tracing one exact HTTP call and understanding when it hits which part of the system exactly is very, very hard. And I have very, very seldomly seen that done. So it's actually close to impossible. So the practical model that I use for this talk, and I think is valuable here, is to think of these systems as a queuing system with a hidden queue. So you have a client that makes requests, and you have a lot of queues which you don't really see, but theoretical, you can just think of it as a big queue. And then you have a server which then services the request and sends a reply. You also have queuing on the way back, but usually that queuing is less relevant than the queuing on the way to the server. So for the purposes of this talk, I'm ignoring it, but of course, further investigations may be a good idea also on this part. Here's how the the abstract model looks like. So for a client-server interaction, you actually have two spans. One on the client side, which we'll call response time, which is the official name in queuing theory. And then there's the service time, which is the time on the service that the server spends to process the request. And here everything is nice. The client span actually encompasses the server span. This doesn't have to be the case. They can be they can look very different, the service time being much further out. But this is a good case. And what's the difference? So we have in the real world also queuing systems. And so the difference between the response time and the service time is actually very, very significant here. If you are waiting on the bus line, the service time is the time that the bus driver is taking to stamp your request or sell your ticket. And the response time is what observed on the client. So if you're entering the queue and then until you have your ticket and taken a seat or gone back or whatever. So that is a very, very significant difference. And in practice, we care a lot. But in computer systems, of course, we should also care if we are really seeing the queues. So there's an engineering trade-off here to make. You have this client on the one side, and you have a server on the other side, and maybe some networking gear in the middle, maybe not. You can either measure on the server, then you will only get the service time, and you have to see how much you can do with that. But it's comparatively easy to implement because it's only one component. And then you have the client. Client can be easy if you have a single client, but can be very, very complicated if you have like mobile devices or some uncontrollable set of clients. So it's harder to implement, but of course it's much more meaningful if you directly observe the latency that your clients are experiencing and not just what you're seeing inside the server or inside the bus. And there's an interesting avenue to explore to exploit network intermediaries to get more latency information. So API gateways and load balancers can be used to extract latency, and then the question is, how close are you to the client? How close are you to the server? And how that looks is, of course, up to the exact system you are using, but typically it's not so far from the client, at least if there's no network partitions or stuff like that. So you maybe have a chance to do something here without instrumenting all the clients. So the sad truth, and maybe this is the biggest takeaway that you should have from this whole talk, is you cannot measure response time on the server. You can only measure service time on the server. Because you're on the server, you only see the server. So basically, if you're on the server, you are inside the bus and you cannot see the end of the queue because the queue is hidden from you. And so yeah, this is the sad truth here, which underpins all the difficulties we will see. And so also Jean's talk goes a lot of length about showing latency information that is captured on the server and on the client and how those things differ, or how you would actually like to report on certain things. And for this occasion here, I actually wrote a little simulation to exemplify all of that, because every effect that was discussed in this talk and we have discussed here is actually very accessible to simulation, and we can see what happens here. So as I said, this is our theoretical queuing system. We are simulating here a client which sends 10, like a varying amount of requests. And then you have a server which has 10 workers and 10 millisecond service time per request that each worker is servicing. So it gives us total capacity of 1000 RPS. And then we are monitoring the client side and the server side with best practices. And yeah, we use use and read and all this kind of things. So we're looking at the request rate, we're looking at the concurrency, how many active requests do we have, and we're looking at the latency, like the response time on the client and the service time on the server. And the server, we also have the request rate, which is in this time called the arrival rate. Then we have concurrency. Here it's how much active requests we have in the server, so many active workers we are currently having. And yeah, the service time. Service time here is always constant because we said every request is taking exactly 10 milliseconds. Practice, this is not true. An overloaded system might actually have a longer service time, but it's actually not that bad of an approximation. So we will use it for now. If you have maybe a strict CPU-bound workload, it might actually be completely constant. So here's how the system looks under very low load, 50%. The request rate is 500 requests per second. The arrival rate is also 500 requests per second, so there's actually no difference. The concurrency, you have 5 requests being active at every point in time, and the concurrency on the server side, you have 5 workers being active at every point in time. It's also very, very similar. And latency, let's look at the server first. This will be always the same picture. We have exactly 10 milliseconds here for the server. And for the client, I'm seeing a little bit more. I have 10 milliseconds, and then I have maybe 12 to 15. And what's plotted here, these are percentile metrics. I actually choose the P50 and the maximum here. Usually you would probably have P90, P99 as well, but P100 is even more sensitive than all of this. Just to simplify it a little bit, you see the median latency, which is just where the body of latency is, and then we see the extreme outliers as well. So you have actually a fairly good picture of how latency behaves. So now we are pushing the load a bit further. So 90% capacity, still request rate and arrival rate look similar. Concurrency, yeah, sometimes we have some queuing going on. We start to see that, and the utilization is pinned at 10, but the concurrency might go up a little bit more. So we're seeing a slight difference here, but very similar. And then the latency, again, we have this flat line here, but we're seeing more and more latency coming up. Percentiles are starting to grow. 99% capacity, similar picture. We start to really see some queuing delays. Here, a request took like 250 requests were active. And similarly, we had to wait 250 milliseconds, almost, 250 milliseconds, I think, until we cleared the queue here. So, yeah, starting to misbehave on the server. We're starting to hit some flat lines here at the capacity limits, but it all looks fine. Latency is still good, and this kind of picture started to diverge. At 100%, this is complete difference. Arrival rate is pinned at 100%. Utilization is pinned at 100%. Service time is still flat, and request rate, okay, we tuned that to 1,000. We see pending requests going up very much, and the latency is also growing. And when we are pushing the system over the top, then we really see some weird things happen. We're seeing unbounded growth of concurrency and the latency percentiles. So here, really, things are getting complicated. Here's one toy example, just for the fun of it. If you're pushing a system dynamically against a limit or over a limit with a kind of a hockey stick curve, then you see an arrival rate tops out here. We see how the queuing starts really to kick in, and then we have the burn after, where we are running through the requests, and we see a latency profile which starts to be pronounced even later. So you can look at this a little bit and see, okay, well, then when those requests which have waited in the queue quite a long time, then they are arriving, and you have request latencies which are just insanely high here. But this is like the theoretical behavior of all that. Stall system, and this is probably the most interesting here, is if you are stalling the server for a certain amount of time, this is what you see on the server. See no request arrived, you see constant utilization, and you see no latency. And then you see a single or a few requests which took very long, but this is only visible if you see a maximum, if you use a maximum. And the other P99 or something like that would still be unaffected by that. And this is like very common with the GC situation or something like that you have stalled systems. Of course, the client observes all these things. You have a growing amount of queuing, and you have like this backlog of requests which are waiting in the queue, and you're seeing how they are burned out. And so usually your latency metrics are pretty blind to this kind of stalling that happens on the server side. This is the core of Jill's talk, understanding that picture and how that arises in benchmarking situation. So coordinated omission, the concept is about hidden coordination between the load generator and this system under test that is blind, that actually is making you confuse service time with response time in certain ways. So the easiest way to do it is to automatically back off once the server falls behind. So you stop sending requests. So you are basically just eliminating the queue by stopping to send. So you will never see the kind of growth in the queue, and thereby also underestimating your load and your latency profile. And a second thing is if the server is stalled and the client stalls as well. So if your load generator is running in the same process, then you will also not see this, because you have this kind of hidden coordination between the two. If you stop the one, you will also stop the second. So that's the reason why yeah, sometimes in micro benchmarking, you're not seeing that. And I cannot do this part justice. I think Jill's talk and Ivan's blog do a much better job at exploring that in full depth. So I will refer you to these sources to see more about it. The last part, how to analyze latency, that will be really quick. So this is just a screenshot from CONF with some best practice examples. I've talked about that at 2 conferences here, which are linked, but I'll just say from my perspective, but I think it's fairly obvious that having histogram information of every single request that was made, every single latency available over time, is giving you all the means you need to analyze latency. And I have not seen something better than that, except raw data. If you can store raw data, of course you have that. But this is a very good compromise. And more systems are implementing histograms. Also, the open source world is getting there. So with that, let me close. Thank you very much for your attention. I plan to write a blog post on this as well. It will be under heinrichhartmann.com/latency. And if you're interested more in statistics and latency information, you can follow me on Twitter to be notified when something comes up again. Thank you very much and enjoy the rest of the conference. Bye-bye.